Better? Yes, great. Exchange cell phone for thing. Okay, welcome back. We are in part two. We will now move to the ultimate part of our arrays, or rather the arrays, which are the ultimate part of our receivers. These are detectors and readout devices. And then we'll talk about systematics control, some survey strategy considerations, and the very basics of how you make a map for the CMB and release some data. So one of the top questions I get is, why don't you use CCDs? And the detector technology between CMB experiments and astronomical instruments like JWST or Rubin, shown here, is just fundamentally very different because they have different properties and are measuring light in different ways. So CCDs are photodetectors that are based on photon absorption and then changes within semiconductor materials, which are between a conductor and an insulator. These make the basis of most of our modern electronics. They are kind of like, but not quite like, the cameras that we have in our cell phones. And they might be cryogenically cooled, but typically not below a Kelvin. They would stop working at cryogenic temperatures. And this GIF in the center shows you how you can manipulate charge carriers within your device here for a CCD, where you change the voltage and kind of move around the charge carriers to read out your signals. I'm sure if you've taken an astronomical instruments class, you've looked at the little cartoons with the photon buckets, with the buckets pouring into the next bucket. So this is just a completely distinct technology from what we work on for CMB experiments. For CMB experiments, we use superconducting detectors, and superconductors just have a totally separate state of operation than semiconductors. These are very unlike anything we use in our phones or day-to-day life because they rely on sub-Kelvin cooling and are useful for continuous measurements of millimeter and higher frequency radiation that is not optical. Two main types of superconducting detector that CMB experiments are relying on these days are transition edge sensor bolometers and kinetic inductance detectors. Here you can see an array for both of these. They look kind of similar just based on the overall properties from a distance. And that's because they are. Typically, these arrays are fabricated in similar ways on these silicon wafers that are then of a characteristic scale that it's like 150 millimeters or so, maybe a little smaller, maybe a little larger, not larger, smaller. And then you tile these to make up the detector planes of your arrays. When you zoom into them, though, the detector technology themselves are quite different. So we'll talk about the basics of each of those. One thing that they do have in common, it's not the most perfect comparison here, but you can see kind of a polarized shape, like X's in both of these. That's because both technologies are polarization sensitive, and those antennas are what cause your polarization sensitivity. So let's start with TESs, transition edge sensor bolometers. These, again, are fabbed on one of those wafers. If you zoom into one of the pixels, we define a pixel as the location that a waveguide coupler deposits the incident radiation and then tunnels it to your detector. So in a single pixel, you might have multiple detectors themselves. So the antenna are the big things here. That incident power is then coupled to your actual transition edge sensor, which is this tiny little piece of superconducting material in the middle of this larger island that is then weakly coupled to your thermal bath through a variety of other materials. Aluminum manganese is one of the materials we use for TESs. You can use a variety of materials. These material choices are driven by how simple it is to manufacture these arrays, the critical temperature of the superconductor, other characteristics about its resistivity, and the way that you're going to be using these when you're operating them on the sky. They'll have different properties. So this is what that looks like. All TESs are going to be sub-Kelvin operation. I think there might be higher temperature ones, but in modern CMB experiments, these are all at millikelvin, hundreds of millikelvin scale. We use their critical temperature as the way we read these out. So a material that is a superconductor will have some normal resistance at higher temperatures. If you cool it down past its critical temperature, it will suddenly lose all of its resistance and go superconducting. That's down here. And it's on this transition that TESs become very useful, very sensitive thermometers, because if you were to make a very small change in temperature here on the x-axis, it will result in a large change in resistance, giving us the ability to read out small changes in temperature. So then we use that by weakly coupling the TES to a thermal bath in our coupling scenario with a dilution refrigerator. And the power incident from the sky hits those antennas, is funneled through to this material, heats it up a little bit, and it's constantly in balance between the incident radiation and the bath. We need some device to read out TESs, and we typically use superconducting quantum interference devices, or SQUIDs, and we'll talk about that in a little bit. Readout is an important consideration here. We talked about this house metaphor before and how you don't want too many wires to be going in to heat up your system. And this is where multiplexed readout comes into play. We cannot put in one wire for every detector. We would easily overwhelm our system. So we need to read out multiple signals from different detectors on each wire, and that's what we call multiplexed readout. So SQUIDs are used to read out TESs. They are sensitive ammeters. The changing flux through this loop of a SQUID will change the current running through the SQUID. A SQUID is one of these Josephson junction devices where you have some superconducting material interrupted by a small weak link of non-superconducting material before returning to a superconductor. And we couple them then through these magnetic sensitivity properties to our transition edge sensor readout loops and achieve multiplexed readout. Here you can see a penny with one of our SQUID chips. So these are very small devices, just like the TESs are. There are two main schemes of multiplexing. One is time division multiplexing, where you are creating a series of switches with your SQUIDs. And the rows of detectors are read out one by one. So you're reading a bunch of detectors, and then you're turning that off and reading the second bunch of detectors, and you're turning that off, et cetera, and doing that many times. There's another scheme called frequency division multiplexing, which reads out all of your detectors all at one time. And it does this by creating a series of resonator tones. So you create a tone going in and out, and it reads out in frequency these combs of resonators that then drift around in frequency space when coupled to the transition edge sensor, because that current is changing, the RF SQUID current is changing, and you're continuously monitoring these small changes in frequency space. Switching now to kinetic inductance detectors, these devices are not sensitive thermometers, but use the principle of superconductivity in a different way, where you have some Cooper pairs in a superconductor. Incident photons hit the Cooper pairs and break them apart into quasi-particles. The change in quasi-particle density changes the inductance of the device, and then you put this inductor into an LC resonator circuit. And that change in inductance creates a change in frequency of the resonator circuit, just like the frequency division multiplexing scheme I just mentioned. So kinetic inductance detectors have the benefit of not needing SQUIDs at all. This is dramatically simpler than the TES scheme and means that these devices are essentially their own readout devices. The fab considerations are pretty much the same. You can make kids out of different materials. You can, depending on what kind of transition temperature you're looking at, tune that material, try to optimize for efficiency. And one thing that I like to point out in this picture is if you look at the frequency of light that you're trying to observe, naturally your lower frequencies are going to be bigger. And I think that's just fun when you look at the lowest frequency pixels in both transition edge sensors and in kids. They just become really large, and you can easily see those antennas by your eye, and that's just having to do with the wavelength of the light that's hitting them. Okay, this is a slide. Has too much detail for this, but I wanted to throw it on here. This is what an exploded view of some of the packages for the kinetic inductance detectors for CCAT look like. There are many mechanical structures that make up a detector package. One of those elements here is this kit array shown in this kind of gray hexagon. The rest are either mechanical structures supporting that or the feed horn stack, which I will not talk about next, but shortly. These are waveguides that couple the light to the antenna of the array. Up here is a detail view. It shows you what the antennas look like, the absorbers for these systems. And the crossing is giving you the polarization sensitivity. So you have this sensitivity to light polarized in two different directions. And then across your array, those will be at different angles, giving you complete polarization sensitivity of the array to light. That means that one detector might be coupled to one polarization and another to another, and that's how you read out those signals. By contrast, you can compare to transition edge sensor packaging. Do you notice all this stuff back here? This is an S4 module. These are our squid chips. So suddenly our packages are much more complex if we use transition edge sensors. The reason that we are still using transition edge sensors is because they're the state of the art. They've been tested. I guess state of the art means not tested. They've been very well vetted. Kids are a newer technology. We are just starting to understand them, and so there's more risk associated with that. So stage 4 is baselining transition edge sensor bolometers. The Simons Observatory also uses squid readout, but in a different configuration, so a little bit more compact, and it's in this modular structure that is similar to what the CCAT ones look like. But it includes these arrays of squids that we don't need for kids. Okay, so these are the feed horns in cross-section that I was talking about. There is another choice for a waveguide, which is these sinuous antenna and lenslet couplings. So you choose your waveguides based on what kind of antenna you're using. So these sinuous antennas are another type of waveguide choice that aren't these crosshatch antennas. They look so beautiful, in my opinion. These are just simple, you write down the incident wavelength, like light equations, and couple them to geometric shapes, and that's what creates your antenna. And then depending on your antenna, you choose either the feed horn or the lenslet. And the antenna choice will influence your detector's angular response, the polarization properties of the light you're looking at, as well as bandwidth and efficiency. And like I said, with the cross-hatching, the antennas are always designed to have a polarization symmetry so that you can completely cover polarization across your array. And the challenge with feed horns is sometimes when you're going to these high frequencies, they're really difficult to machine. You just have to make so many tiny, precise cuts in metal that it becomes challenging to make out of one piece. One way around that is to use a stacked feed horn array where different slices are cut to different diameters and create this shape that you see in cross-hatching here. Bless you, bless you. Lenslets are also hard to manufacture because you need to have some kind of an anti-reflection coating on each one of these tiny little domes, and it's difficult to get that right as well. So both of these are, present their own challenges and pros and cons, and both will result in a good detector system. Okay, so we talked about why multiplex readout is required to not overheat our system. We've also talked about time division and frequency division. These are just more pictures to back this up. Up here you can see one of these squid chips. These are an electrical diagram showing you the rows turning on and off for the time division. These are the frequency combs we talked about for frequency division. And I don't think we need to spend too much time there. By contrast, I will say that KID readout is rapidly being developed, but is still less mature than squid readout. So while kids are naturally frequency multiplexed, the readout, just physical scheme here, still requires quite a deal of engineering with regards to strip lines or cables, the physical components that support all of these things, and then the readout that is being constructed to take these signals and turn them into data. So within the community, there is a great deal of development of software for both types of readout. The Simons Observatory, which uses frequency division multiplexed squids, is working on software that has been now updated for and related to KID readout development. And the majority of these things have some kind of local electronics that are coupled to the physical readout system of your cryostat. They create some kind of a detector time stream. So all of our data from these detectors is taken in time space. You're continuously reading out your signals. It does not at this point look anything like the finished CMB maps that we're all used to working with. It's then relayed to your local computers and then eventually to your long-term storage where you can then use it for your final map products. Okay, pivoting to systematics control. There are a number of not detector-based, instrument-based modes of controlling for systematics that you can put in physically into your system before you have to deal with them analytically in your data. One such device is a polarization modulator, and this creates a consistency check by injecting some repetitive signal into your instruments where you can mitigate systematic errors that might be present from your instrument. This includes things like beam errors, if you have some polarized pixel detector differences, or the temperature to polarization leakage that might take place in your instrument, as well as polarization coupling and atmospheric noise that might be polarized. You can avoid the construction and engineering associated with these modulators by either exploiting Earth's rotation to your advantage or rotating your entire instrument or telescope. So here you're looking at a variety of spinning half-wave plates. These are really impressive things. You can have them either be cryogenic or room temperature, and essentially you just set up a system that spins a plate and creates this signal in intensity in time. This is an example of boresight rotation. If it loads, definitely don't want the volume on this because it's so loud. Oh, come on. Oh no. I don't think it's the plug and unplug this time. Not sure what's causing it.
It's your laptop. Do you need sound in that video?
No, we don't want sound. This has never happened with this before, so I'm curious.
You gave up?
It just gave up.
You try to escape.
Yeah, didn't work.
Yeah, this is a laptop.
I guess my laptop has just gone dark. Try to turn. Oh, okay. Oh, weird.
I need a full restart.
Yeah. Okay, we're restarting the laptop, everyone. Sorry. It's going to be an issue. This is a brand new laptop.
Yeah.
Apologies.
No. No, it was something when you try to play the video, right? Yeah,
It did. I don't know what the difference was from last time, though. Don't install Zoom updates.
Oh, yeah. You do that at the most inappropriate time.
Yeah, it does.
Right 1 minute before the meeting.
Sure.
Don't need, yeah. You can just skip that link. That's required.
Yeah, I mean, Zoom doesn't want to hit.
Okay. Now it's working. Hopefully.
Just have to select that.
Up. All right, we're back. Wow, much anticipated video for just a little rotation. But here it goes, it's rotating. So this is bore sight rotation. It's when you rotate your whole instrument slowly to mitigate systematic errors. This is a good choice for when you don't want to put a spinning half-wave plate in every single optical path of your camera or have an absolutely massive 2-meter one in front of all of your arrays. So this too is important for all the systematics I just mentioned, and it's important to say also it's great for controlling leakage that might influence your B mode measurements, which we mentioned are very sensitive to systematics. So that's why we go through all the trouble of rotating our devices like this. I will say that this opens you up to issues, right? Like as we just saw, things fail often with technologies. When you're rotating and spinning things, you can imagine how you are taking a bit of a risk overall. Okay, I gave a nod to mirror considerations. ACT is shown here. This used a 6-meter segmented mirror. I think this is another non-intuitive part of millimeter instrumentation. Like I mentioned, looking through the windows and being like, they're opaque, what are you supposed to do? This doesn't really look like a mirror, right? It looks like a bunch of panels of metal, but because of the wavelengths we're working with, it works just fine as a mirror. However, there are some issues with segmented mirrors, such as structured side lobe response from gaps. We've done a lot of engineering to reduce our gaps, but you still need some amount of gap because these things are expanding and cooling expanding and contracting with temperature fluctuations during the day. For example, you also need to just install them and focus them. So you need some gap present, and this creates some issues to contend with. You can get away from that by using a monolithic mirror, but then you're sensitive to, no, I don't have a picture of one, sensitive to variations in that mirror surface. And you also need to deal with thermal deformation in the mirror and gradients that are responded to in different ways in the mirror surface. So there's pros and cons to both of these technologies. One thing that might be useful to you if you're working with CMB data products is that you might encounter maps that are daytime versus nighttime maps. This is part due to systematics that come about because of the hot sun during the day changing the mirror properties. There are other elements that go into that as well, but in CMB land, we can observe just as well daytime and nighttime, but there are differences in systematics that come into play. So then you have to think about observation fields. Once you have your system working end to end, you've considered your systematics, you're all ready to go. Now, where do you look? We've talked at length about why we want to observe or avoid the galactic plane for your deep regions. You minimize your foreground when you go to these cleaner areas, as you can see here in field selected for biceps B-mode search, as well as SPT area that you just saw Ian B-mode maps from yesterday. This is trying to avoid the emission associated with the galactic plane. The ACT survey region, as well as the SO and CCAT survey regions, do contain galactic plane, but the deep focused patches are away from the galactic plane, so you get these kind of funky shaped maps that avoid that fiery arc in the sky. And then as another consideration, you want to maximize your overlap with other surveys depending on your science goals. So here too, you see the survey areas from various optical experiments. We talked about why cross correlations are exciting. We want to look in the same places. And then when you're doing more targeted science surveys, sometimes it's better to observe a smaller area and go deeper. And that's where selecting areas that might have astrophysical objects of interest or high degrees of overlap with other frequencies of surveys might be exciting. So a lot goes into planning where you're looking. And then you need to think about how you're looking. So as you're observing from the ground, Earth is rotating, the sky is moving, and then your telescope is also moving. You might scan in a number of different ways, the directions you're looking, the pattern you're going, how quickly you're turning around at the ends of scans. Those all need to be considered as you're creating your observing strategy. You also need to make sure you're not looking directly at the sun, for example. So you need to avoid the sun, you need to avoid the moon, and you need to be able to stop your strategy and start looking at, for example, a planet if you want to do a calibration observation. So in general, CMB experiments that are wide field surveys like this will pan across the sky in some kind of a pattern, and that pattern is optimized for the resulting map depth, as well as cross-linking. You can see that here. Cross-linking is scanning while the sky fields are rising versus setting. So it creates this kind of paintbrush effect where you're like looking like this, and then you're looking like this. And that's important to reduce your systematics. So when you see maps of depth coverage here, you're looking for cross-linking and overlap that will give you lowest possible noise and systematics with your final maps. In the end, you don't get 24-hour perfect observations. You get something that looks like this. This is ACT's observing time, integrated time, starting from 2013 and then going to 2015. We, of course, observed into the 2020s. But here you can see there are times during the year that you don't observe at all. And sometimes the weather just makes it not advantageous to observe because there's so much snow or water vapor happening that it's not going to be great seeing. And then during the day, you have to pause and do your calibration. You have to check your detectors, maybe do some other checks for the instrument. That's going to take away from your total observing time. And different arrays might come on at different times. For example, here you can see we go from 1 array to 2 to 3. So the colors change in terms of how many detectors are on the sky at any point. And then here there was a half wave plate that was introduced in the crosshatched region. And you might have some incomplete coverage of various systematic mitigation approaches. So those are some of the realities. Other realities are that we need to continue to make sure we understand what is happening with the instrument when we're actually making these observations. And there's this laundry list of things to measure and hardware that supports it. We need to understand the beam profiles of our system. This is included in those map products that you might download. We characterize the instrument beam and publish it with the map data because that's what goes into our final data products. And we have to study polarization angles, detector gains, time constants, meaning how quickly does your system return to normal after absorbing some power in the detectors. And I'm not going to read all of these words. You can go back and read all these words. One thing I'll just point out is that this is a planet scan. We do these to check our system both in commissioning when we're first setting up a new instrument and also later to make sure we're staying calibrated over time. There are many data outputs that need to be monitored, recorded, analyzed before maps are made. From the detectors, we get large sets of time-ordered data. We have to do these routine systematics check, like I mentioned. And we have to make some amount of data product to check that what we are seeing is what we ultimately want. So these are often known as quick look maps or quick look data products. These are separate from published data. For observations, we have to look at where the telescope is pointing. We need to write down also what the scheduled observations were and keep track of all the information that constructs a model of where the sky, where the observations were on the sky at any given time for all of our arrays. And then for our housekeeping, again, we need to keep track of our cryostat. We need to make sure if something goes offline, we get an alert and can fix it, both in remote observing configurations as well as hardware on the ground, like our compressor turned off, we need to turn it back on. And we make a lot of custom software in order to enable all of these things. I was looking a little bit into data rates. I'll just quote one number, and that is for one single small aperture telescope for the Simons Observatory, which is going to have 5 of these with new telescopes coming online soon. Each one of those creates 3.7 megabits per second per telescope. And that's going to be larger for the large aperture telescopes. So it's a lot of data, we need to store it, and there's a lot of work going into this. I will not get into that work. I'll just refer you to some papers talking about the software and data handling for these experiments. So we'll pivot to map making. This is a very rudimentary way of thinking about map making. I think of map makers as wizards. They work on this in really exceptional detail and work just incredibly hard to make the data products that we all benefit from. But at a simple level, you get some time-ordered data from your detectors, and you want to turn that into a 2D sky map. This means that you need to compress your data volume from roughly on order 10 to the 12 to 14 time samples to order 10 to the 5 to 8 sky pixels without losing cosmological data. You also need, of course, accurate noise and systematics modeling to make sure you're not losing your data or affecting it negatively. So then the data model for the map making problem looks something like you have some data vector, a concatenation of your TODs, and then you have something where you are combining pointing information that has to do with your telescope scanning and the orientation on the sky at a given time, times your true sky signal, which is what you're interested in measuring, plus some noise. One example of a mapmaker is a maximum likelihood mapmaker. This uses a likelihood function that involves an estimated noise matrix, noise covariance matrix in your construction here of this data array and pointing model and real sky observations. And then you can solve this and find a linear least square solution for your actual sky data as defined here with regards to your pointing model and your noise covariance matrix. Iteratively solving this is going to be the solution because you cannot invert all these matrices for your sky areas generally. And you estimate n using various data splits from observation as well as calibration data. To make and manipulate your maps, there is a wide array of publicly available software tools. If you dig into any details in CMB mapmaking papers, they will be citing these. And these are honestly very fun to play with. If we had another day here, I might be interested in going through some of these Jupyter notebooks, but if you are so inclined, you can download these and play with this and learn more about how maps are actually made. And then the final result of all of this is going to be the publicly available data that you can go right now and look at NASA Lambda and download ACT data products, for example, as well as a number of other experiments data products. And you want maps that might isolate certain parts of a CMB map. You can, of course, just have a CMB map, but you can also, for example, have Compton Y maps, polarization maps. Shown here are CMB temperature E-mode, this is a good eye test for me. I should look over here. E-mode polarization maps and Compton Y maps. In order to component separate your maps, you can use either blind or unblind methods that either result, or they all result in component separation, but either rely on models of your data or minimal assumptions and empirical data properties. The example that best approximates the ACT data is going to be this internal linear combination approach, which is one of these blind approaches. This assumes some frequency dependence of your components, but it doesn't rely on a sky model. If you're interested in learning about the ILC approach, there are, especially Will Colton's paper on how these maps are made is recently available in the archive. And so there's so much information I'm chucking into the, and then things happen bin, but things happen, you do this work, and then you have FITS files. Largely, we're working with FITS files and accompany those releases with useful information such as instrument beams, noise maps, other tools you may need for your analysis. So I'll point you towards the ACT products on NASA Lambda if you're interested in digging into this. And I think that is the end. So thank you for being here through these 4 lectures. We have gone through kind of the state-of-the-art questions that are available to us as CMB observers in terms of primary and secondary anisotropies. We've discussed some complications and foregrounds, and then I took you through a whirlwind tour through our instrument to map making and publication. And I hope to see you at more CMB talks in the future. Yay, questions.
Yeah, thank you for the really good talk. I was wondering about the experiments you were pointing, like CCAT and Simons, that both are going to be in Chile and they're going to, serve what are the main differences and things that they can complement and like the time scale? And I have another question, but I can wait.
Okay, yeah, wait on that. Great question. So the Simons Observatory is the kind of newest and most exciting in terms of detector count CMB experiment from the Atacama. It will be on Saratoga, which is the same mountain that was home to ACT. ACT is no longer observing. And the Simons Observatory is deploying 1 LAT. Right now, there are 3 SATs currently in operation, and then we'll have 2 more being added in by our UK collaborators and Japan in upcoming years. And that is expected to give us the best CMB constraints from primary anisotropies to date, as well as exceptional measurements of secondary anisotropies. And the frequency coverage, I think I nodded to it in one of my previous plots. I can get this up actually while we discuss this. Frequency coverage is kind of the typical CMB ranges. So it does not extend into sub-millimeter land. And you can see those bands here in yellow up to green. They top out I think they're going to top out at 280 gigahertz. And CCAT is located in the mountain right next door. SO is currently observing now. We just saw first light this year. CCAT will see first light next year, brand new telescope, Fred Young submillimeter telescope, FEAST for short. There's a lot of terminology here. It will be located at a higher elevation. So the Saratoga site that ACT is observing at is around 17,000 feet in elevation. And Cerro Chachnantor, home to CCAT, will be above 18,000 feet in elevation. This pushes us above precipitable water vapor to a degree that we can extend our frequency coverage to the sub-millimeter. Both experiments will be observing the exact same wide fields. It's the same telescope, just with slightly different optical properties to enable the sub-millimeter for CCAT. And that means we will extend this frequency coverage up for the same areas on the sky, which would be great for cross correlations across the board. CCAT will not be fielding small aperture telescopes, so we don't have sensitivity to B modes, but we can contribute to B mode observations by controlling for systematics.
And my second question was regarding sensitivity and
Sensitivity to what?
sensitivity versus resolution. The way I'm imagining this is like you're saying that, increasing the resolution won't be like helpful if I still have noise there, right? Is that what you meant?
I don't want to say that it's not helpful. It depends on what you are considering. So if you're looking into granular structures, like you want to resolve SZ filaments or something like that, resolution is going to help you. But sensitivity is the thing that's going to improve your signal to noise. So in general, when we're looking at these precision cosmology measurements, we want to improve our sensitivity. And if we're going down to smaller or larger angular scales, lower L, resolution isn't going to get you anything there.
I was wondering if you could speak a little bit more about how in the blind versus unblind, you make sure you're forward modeling in both cases. Just because it seems like if you're fitting a model to a data, I know in interferometric experiments, people will use sort of like a redundant calibration, something more iterative, but how do you do that for a single dish observatory to make sure you're not like encoding any confirmation biases into model fitting?
That's a great question that I think requires a lot of nuance that I, as a non-map maker, don't have a fantastic answer for right now. I would encourage you to look at the map making papers. I will say that the fact that it's a single dish, I don't think, yeah, I can't speak with great detail to this, but there's a lot of information happening in the time streams that I think would make it more similar to other types of analysis without regard to the fact that there's one mirror. Yeah, there are 2 mirrors, by the way, just one, but yeah.
Another question on map making. Can you elaborate on when you combine maps, ACD maps with like say Planck, on why exactly that is done and what extra benefits that gives us while combining, because ACD has better beam resolution than Planck, right? So why do people do that?
Sorry, I think I missed a word of this. You're asking about map comparison between maps from different experiments?
I'm talking about map combinations because in the Lambda website, there's ACT plus Planck combined maps,
Why we
right?
combine data sets.
Yeah.
So there are relative strengths between the experiments. Planck is a space-based mission that has better low L observations, for example, but worse high resolution, and ACT has the benefit of being high resolution. When you combine the two, you are essentially combining the strengths of both of those experiments. And so we do compare the data from just ACT alone to make sure that we're not introducing anything that is in disagreement with ACT-only results. But in general, co-adding these things just improves our measurements across the board by incorporating the strengths of each.
Thanks.
Just a simple question on observing strategies. Can you elaborate the point of either observing large sky area with shallow depths or small sky area with larger depths, and how it is related to the science goals of CMB?
Yes, definitely. Let me get the maps up so people can visualize them. So you only have so much time. We all only have so much time on this earth. And for an experiment, you only have an amount of integration time that you have to spend in any one area. To improve your sensitivity or your just noise properties, you can reduce the amount of area you're looking at and integrate down in that signal. So in general, even when we are doing the wide field areas, we have, for example, in this ACT region here, an area of that we deem to be the higher depth region. And that's where we're going to get our best systematic statistics because we're spending more time there. Typically, those are chosen to have the best systematics, meaning we're away from the galactic plane, we're in the cleanest area of the sky, and that's basically our primo data. If we had infinite time for this, we could do that everywhere. But the reality is you only have so much observing time, so you want to spend it in the best sky areas that might also have the best overlap with independent catalogs that you are cross-correlating with. Did that completely answer the question, or is there another part?
Yes, but if you think about noise, that's large area with shallow depths. The noise amplitude is the same as small area with deep depths.
The noise is the same as, so.
And I think if you observe deep area, the only noises come from instrumental systematics, and that's why you are improving.
The deep areas are also selected to have lower contamination from systematics as well. So typically you're not going to get the best measurements in wide areas because there are other impacts at play. Also, the more you integrate, the more you're reducing things like atmospheric noise and any other systematics that might be time varying, you can average those down.
Thank you for the great talk. I'm wondering about if there's a degradation of like the actual instrumentation with respect to time, and if that induces some like systematic effect on observables in some way.
Ooh, that's a great question. So one part of this is that experiments are constructed with a lifetime in mind. Typically, this lifetime is within, you think of a building kind of like crumbling and falling apart in time. The experiments are typically like 5 years at a time, so things aren't going to be degrading super quickly. In general, the degradation of the internal parts of the cryostat are minimized because you're in this very high vacuum and very cold environment where thermal cycling is something that causes us issues. Things might break because they're expanding, contracting over and over. Stresses and strains are present. Maybe you're changing the material properties a little bit. But even if you were to change and degrade your thermal conductance of your temperature links, for example, you can correct for that when you're biasing these things to make sure you're still operating in a regime with these calibration checks where you're always testing your detectors, you're always measuring your responses, you're keeping an eye on it to make sure that you can correct for that some types of degradation, and then others like oxidation aren't taking place because there's no oxygen, we pump it out. So there isn't a big dependence on this that we keep. It's not like we're watching our experiment kind of slowly crumble and needing to adapt for that, thankfully. But that's a really good question.
Thank you.
All right, let's thank Eve one more time.
Thank you.
So we have a little bit of a longer break, but let's shoot to be back here at 11 o'clock if possible, 20 minutes-ish. And we'll start with the next session.